Okay, so today we're going to take a look at acceleration. So in our last lesson, we spoke about how the first derivative could be found when we're given problems that deal with either the word velocity or instantaneous velocity. And in a previous lesson, we also went over not only do we find first derivatives in our course, but we also find the second derivative in our course. So what the second derivative would be in these types of word problems would be acceleration. So that's you're basically seeing over here, okay, that acceleration, a of t, is a function of time, is the derivative of velocity with respect to time. And here's the notation for a second derivative, d squared s over dt squared. So it's the second derivative of position with respect to time, okay? So again, I'm going to give you a second to write this down and what else is being said here. The rate at which a body's velocity, the rate at which a body's velocity changes and measures how quickly the body picks up or loses speed. That's acceleration, okay? And so again, that's our second derivative. Okay, so it says here, a particle moves along a line, okay? So it's moving along a line, not a curve. Okay, so here's your particle. Maybe it's moving this way, maybe it then turns around and moves that way, or maybe perhaps it was here and it's moving there and then moving back. So that way you get used to more of these problems that we see where a particle is moving along a line. And it could be a particle, or you can see the word body. It doesn't matter. It kind of is the same application. All right? So a particle moves along a line so that its position at any time t is greater than or equal to 0. So that's wherever it is for x. Okay, wherever it started is when t is equal to 0. Okay, so then maybe it moves here, and then maybe it moves here, and then maybe it moves there. So it changes position back and forth on the line, depending on what t is. Since t is time, that's why it says t is greater than or equal to 0. Okay, so its position is given by this function, s of t. Now you can see that it is a curve, but that's not telling you that the particle is somehow not moving along a line. Okay, it's still on the line, but where it is, okay, on the line is given by s of t. Okay. Now, it says here s is measured in meters, so that's important for later, and t is measured in seconds. Okay, so always look at the units in the problem because sometimes they're different types of units. Okay. For part A, it says find the displacement during the first 5 seconds. So this goes back to our previous lesson that we went over about displacement, okay? And the displacement is the change of s. So when it says the first 5 seconds, then that means you're going from when t is 0 to when t is 5. So plug in the 0 and the 5, or actually the 5 first, and then the 0, and subtract them. Okay, be careful if there's a different types of displacement, let's say from when t is equal to 2 seconds to when t is equal to 5, because then you would have a different answer. So for part A, we find that the displacement would be 12 minus 2, and that is 10. So we want to say 10 meters because s is measured in meters. Okay, so let me erase some of this ink because it's getting a little sloppy in the problem, and we're up to part B. Okay, so part B says to find the average velocity. So again, we've done this in a previous problem, and it says the word average, okay? We're not looking at instantaneous velocity or velocity. You're actually just doing your difference quotient. So we actually already found the numerator part of it from doing displacement. It has a change of s, and we just need a change of t. So in this particular part, we need to take the 10 we got from doing a change of s and divide it by 5 minus 0, okay? So that gives us 2, and this is in meters, this is in seconds, so we want to say 2 meters per second. And that's part B. So we're up to C. Okay, so C, now this one says instantaneous velocity when t is equal to 4 seconds. So it's the instant where t is 4 seconds. And velocity, or instantaneous velocity, means we need to find the first derivative. So the first derivative, s prime of t, is actually v of t. That's what we need to find. So if s of t is t squared minus 3t plus 2, then s prime of t, or v of t, is 2t minus 3. So now we want to plug in 4 wherever we see t. And this gives us 5, and this would be in meters per second, okay? And if it's a positive 5, so let's go on to part D. So D asks to find the acceleration. So that's where acceleration is going to come in. So acceleration is the derivative of your velocity. So we could write v prime of t, okay? Or we can even write, let me erase this. Let me go back a second. It is the second derivative. It's s double prime of t, which is v prime of t. This is acceleration, okay? And so if we're finding acceleration, look back at what we wrote v of t to be, because we need to take its first derivative. So v of t we wrote as 2t minus 3. So that means if I take the derivative here using the power rule, I get a of t to be 2. So it actually doesn't matter what value of t, but a of 4 is 2. And we're going to say it's 2 meters per second squared. Okay, and that's your final answer for acceleration. Okay, and let's see if there is more to our example, which it is. There's 2 other parts. And while we're at it, we get to see a little bit more of practice problems. But yes, there's an E and an F. So this is a really good example because it ties in with our previous lesson as well. And this is really good because it kind of ties into what I was explaining in the beginning. So E and F. E says, at what values of t does the particle change direction? So I already went over about how the particle is still on a line and how it could go back and forth, how it can change direction. When you have to change direction, you have to stop. So that means that your velocity becomes 0. So if v of t is 0, that means I have to take my 2t minus 3 and set it equal to 0 to solve. So t is equal to 3/2, and this would be in seconds. So at 1.5 seconds, my particle changed directions. Okay, so whatever was going in is now going the other way. Okay, so now part F. So in part F is, where is the particle when S is a minimum? So again, the particle is still moving along a line, but S is a curve, and you can see it's a parabola and it opens upwards, so it does have a minimum point. Well, if you remember, our minimum point for S is where you have a slope of a tangent line to be 0. So if you do remember that, you basically are taking the derivative of s and setting it equal to 0. Well, the derivative of s of t is s prime of t, which is v of t, and we already set it equal to 0 in part E. We found the answer to be 3/2. So where is the particle when s is the minimum is, well, what s is. So we're going to take the function of s. Let me actually clear this out so I have space to do it. And we're going to plug in 3/2, okay, or 1.5, into our function and figure out where that is occurring. Okay, so if we simplify this, we get -1/4, and this would be in meters for this problem. And that's our answer, okay? That's where it is for us. So our position is at -1/4 meters. So I think you're ready to go. All right, so start working on your practice problems and let me know if you have any questions.